Hello student, today we are going to discuss about the moving coil galvanometer. In our last class, we discussed the working or theory of the moving coil galvanometer. What is the topic? Can you remember the topic? This is the topic torque acting on a rectangular coil. Have you seen the topic? The torque acting on a rectangular current carrying coil placed in uniform magnetic field. Torque acting on a rectangular current carrying coil placed in uniform magnetic field. So this is a diagram. So this was the rectangular coil, is not it? So these dotted lines are the magnetic field. These dotted lines are the magnetic field. Have you seen the dotted lines? These are the dotted lines. These are the magnetic field. And this is the coil. And this is the outward normal. This dotted end cap. This is the outward normal. This is the outward normal. This is the outward normal. This outward normal makes an angle phi with respect to the magnetic field. Okay? What is the expression of torque? What is expression of the torque? Expression of torque is this. Torque is equal to NIAB sine of phi. What is N? Total number of turns of the coil. What is I? Current through the coil. What is A? Area of the coil. What is B? Magnetic field induction. And this is sine phi. And also we discussed that when phi is equal to 0, sine 0, 0, therefore torque is 0. So this is the situation of zero torque. Here, these solid lines, this solid line, these solid lines, they represent the magnetic field lines. You just see, this solid line represents magnetic field lines. This is the plane of the coil. And this dotted line is the outward normal. So here, this dotted line is parallel to solid line. That means outward normal to the plane of the coil is parallel to magnetic field. So phi is 0. So therefore torque is 0. So under this situation, no torque act on it. That means under this situation, magnetic field lines passes normally through the coil. Have you seen it? These lines, these solid lines passes normally through the coil. So if this is the plane of the coil, so these will be the lines of force. The lines of force will go in this way. Okay, so under this situation, no torque act on it. Now, what is the expression of maximum torque? When phi is 90 degree, sine phi 1, so torque is maximum. So this is the situation. Here, these are the solid lines. These are the solid lines, they represent the magnetic fields. And this is the rectangular coil. Have you seen it? And this is the dotted line. This dotted line is like this. Actually, these dotted lines represents the outward normal to the plane of the coil. So under this situation, angle is 90 degree. So this is the plane of the coil. This is the dotted line. The pen represents the dotted line here. So these solid lines are the magnetic field lines. The angle is 90 degree. That means if this is the plane of the coil, say this, my hand is the plane of the coil. This is the outward normal. Red pen is the outward normal. And this black pen is the magnetic lines of force. So under this situation, maximum torque act on it. That is, the plane of the coil is parallel to the magnetic field. When plane of the coil is parallel to the magnetic field, outward normal to the plane of the coil is perpendicular to the magnetic field. Under that situation, phi is 90 degree, so maximum torque act on it. So this is the situation. This is the plane of the coil. Solid line is the magnetic field lines, and dotted lines is the outward normal, so maximum torque act on it. Okay? With this theory, we want to construct the moving coil galvanometer. It is a moving coil galvanometer. Before going to the moving coil galvanometer, again I want to study some of the important cases of that maximum torque, that torque. What is torque? NIAB sine of phi. We know that sine phi is a harmonic function. Its maximum value is 1. When phi is 90 degree, sin phi is 1. But when phi increases from 0 to 90 degree, or when phi changes from 90 degree to 80 degree, 70 degree, or 100 or 110, 120, value of sin phi decreases. So as a result, torque decreases. If a less torque acts on the coil, our sensitivity of the instrument decreases because we cannot measure a low current from it. If current is low, again torque is low, what is sensitive instrument? If we measure a very low current with the help of instrument, our instrument becomes more sensitive. So in order to, or when we can measure the current? When for low current, larger deflection is observed. So in order to achieve larger deflection, torque should be more. Therefore, in order to get more torque, the sin phi should have larger value. So in order to achieve sin phi is equal to 1, for certain position of the coil inside the magnetic field, we are using the radial magnetic field. You just see, so this is called a radial magnetic field. We are using the concave pole pieces. Why concave? Because lines of force always originates normally from the surface of the North Pole and terminates normally on the surface of the South Pole outside the magnet. That originates normally from the surface of the North Pole and terminates normally on the surface of the South Pole outside the magnet. So therefore, since it is a concave, the lines of force will be like this. Lines of force will be along the radius of the curved surface. Therefore, it is called radial magnetic field. So this is the initial position of the coil. This is the initial position. At this position is parallel. Initial position of this plane of the coil is parallel to this magnetic field lines. Therefore, any outward normal on it makes an angle 90 degree, so maximum phi act on it. And due to this torque, the coil get deflected from here to here. As the coil deflected from this position to this position, so this is the plane of the coil. Again, this plane of the coil is parallel to these field lines. So outward normal at this position is again 90 degree, so maximum torque act on it. Again the coil get deflected from here to here. Again the coil get deflected from here to here. Now this is the position of the coil. This is the outward normal. This outward normal again makes 90 degree with these lines of force. Again maximum torque act on it. That means when we use a radial magnetic field for certain position of the rectangular coil, we get sin phi is equal to 1. That is maximum torque act on it. Again, if the strength of the magnetic field is large, then also torque is large. In order to achieve a greater capital B, we use a soft iron cylindrical core, because soft iron is a ferromagnetic material. This soft iron is used at the center of the radial magnetic field, and over the surface of the soft iron, the coil is wrapped. So this is the coil. These are the turns of the coil. These turns are wrapped over the surface of the soft iron. As a result, magnetic field becomes a stronger one. Okay. Now we returns back to the construction. So these two are the north pole and south pole of the radial magnetic field. North and south pole of the radial magnetic field. This is the soft iron core. Over the surface of the soft iron core, this is the rectangular coil. This is the pointer. I think you have seen a pointer in every galvanometer. This is a scale. This is a circular scale. This is the zero mark. That means when no current flows through the coil, the plane of the coil is always at this position. The plane of the coil is parallel to these central magnetic field lines. So under that situation, this is the pointer. So this pointer is at the zero mark of the scale of the galvanometer, circular scale of the galvanometer. Now as soon as the current flows through this coil, the coil get deflected, so pointer also get deflected. So from the deflection of the pointer, we can conclude that a current flows through the coil. And this deflection of the pointer can be measured with the help of this particular scale. But if nothing is done, then what happens? Due to this torque, the coil gets deflected, and that deflection gradually increases and the coil makes 2 or more complete rotation about the axis. If nothing is done, due to this torque, what happens? The coil gets deflected and it will make 2 or more turns. It will make 2 or more turns about the axis. So our purpose will not act. Our purpose will not work under this situation. Therefore, a spring is attached to it. So this is the spring. As soon as the coil rotates, due to the torque acting on it, due to this torque, tau is equal to NIAB. When the coil rotates, this spring gets compressed. As a result, this spring gives a counter torque. To the deflection of the coil, and ultimately an equilibrium is achieved. Is it clear? Now I simply give you a little bit of construction from my notes. The galvanometer consists of a coil of many turns free to rotate about a fixed axis in a radial magnetic field. How the radial magnetic field is obtained? Have you seen it? Obtained by using concave magnetic pole pieces. The coil is wrapped around a cylindrical soft iron core, which can also help the field to remain radial in all positions of the coil, and also make capital B strong, because soft iron is ferromagnetic material. Now, when a current I flows through the coil, the magnetic field exerts a torque on it. What is this torque? NIAB sin phi. Since the field is radial, hence outward normal to the plane of the coil is perpendicular to the magnetic field at all positions. That is why phi is 90. So sin 91, so therefore maximum torque act. And due to this torque, the coil gets deflected. A spring S. Have you seen the spring? So this is the spring. This is the spring. Have you seen it? This spring S. A spring S provide a counter torque. That means the opposite torque. K theta, that balances the magnetic torque NIAB. This is the deflecting torque. Due to this torque, the coil gets deflected. When the coil deflected, the spring gives a counter torque K theta. If this deflection is more, theta is more. This theta is measured by the pointer. This theta is measured by this pointer. Have you seen it? The theta is measured from this pointer. So this is the initial position of the pointer. Say the pointer get deflected like this. So this is called the theta. This is called the theta. So if the torque is more, theta is more. So ultimately an equilibrium is achieved when NIAB is equal to K theta. Therefore theta is equal to NAB by K into I. So K is called torsional constant of the spring. Torsional constant of the spring, which gives the restoring torque per unit twist. Normally, this spring is made from a material, from an alloy called the phosphor bronze. Phosphor bronze. So it has very low value of K. So smaller the value of K, theta will be large because theta inversely proportional to K. You just see N, it is a constant, A, it is a constant, B, it is a constant, K, it is a constant of the material of the spring, therefore theta proportional to I. So larger the current, so larger deflection will be observed. Okay? So therefore, if we draw a graph between current and the deflection, it will be a straight line passing through the origin. So since the relation between theta and I is linear, this galvanometer can be used to measure electric current also, provided initially we have to calibrate the scale of the galvanometer. Since the galvanometer is a coil of many turns, galvanometer has a coil of many turns, therefore the resistance of the galvanometer is very large because R proportional to L. Since the galvanometer is a coil of many turns, it has a coil of many turns, so length of the wire is large, so therefore resistance of the galvanometer is also considerably large. Generally, that galvanometer used in our laboratory, they have a resistance of 50 ohm to 500 ohm. 50 ohm, 100 ohm, it may be 150 ohm. In this range, this galvanometer has a resistance. Okay? With this, I stopped the construction of moving coil galvanometer. Now in this galvanometer, we have to define a term called the current sensitivity of the galvanometer. Current sensitivity. So this is called current sensitivity, theta by I. Theta by I. It is called current sensitivity. Current sensitivity theta by I. That means if the instrument can measure, if the instrument can detect a very low current, if the instrument can detect a very low current, then our galvanometer is a sensitive one. So when we can detect a current flows to the galvanometer, when the coil gives a deflection, if the current is low, in the previous class we found that if the current is low, torque will be low. If the torque is low, the deflection will be low. That means we have to design the instrument in such a way that if a low current flows to the instrument, a larger theta is observed, a larger deflection is observed, and that is called current sensitivity theta by I. So NAB by K. That means to increase the current sensitivity, we can increase the number of turns of the coil, cross-sectional area of the coil. But if the cross-sectional area becomes large, then the galvanometer becomes a bulky one, a large one, size is large. As a result, it is very tough to move from one place to other in the laboratory. Okay? So if the galvanometer becomes bulky, then problem arises in its movement. We cannot increase the number of turns of the coil as large as possible, because as the number of turns increases, the length of the wire that used in the coil also increases. As a result, resistance of the coil also increases. Resistance of the galvanometer also increases. We can increase B. In order to increase B, we use radial magnetic field as well as at the core of the coil. At the core of the coil, a soft iron cylinder is used because soft iron is a ferromagnetic material. By decreasing K, in order to get a spring of low K, we use the material called the phosphor bronze. So this is called current sensitivity of the galvanometer, and with this I stop the lecture here. In the next topic, we try to convert a galvanometer into ammeter and voltmeter. We know that ammeter is an instrument which is used to measure electric current and voltmeter is an instrument which is used to measure potential difference. Generally, galvanometers are used to detect electric current in the circuit. But since this relation is linear relation between theta and I, this relation is linear between theta and I, that this galvanometer can be converted into ammeter and voltmeter. And we discussed this in our next topic.